Okay, the name of the next section is called Vector Operations, and I'm going to show you a whole bunch of different things on this video here. We have two vectors, v and u, and what I have here are the ordered pairs for their initial point and their terminal points. And I actually showed this in the last video, that you can represent these with the component vector, and it's pretty easy to find this component vector. What you do is you just start with the terminal side, and you take the x coordinate of the terminal side and subtract the x coordinate of the initial side. So -2 minus a -4. And now you do the same with the x values. So you always start with the terminal side. -2 minus minus -5. Okay, so this would be -2 plus 4, -2 plus 5, and so we could write this as v here is equal to 2, 3. And so this is actually, I call it the component form. The book calls this the standard position of the vector. So this is the vector, but if I graph this particular ordered pair, 2, 3, let's go over 2, up 3, what I get is I get from the origin out to here, I get this exact same vector, but starting at the origin, going to that ordered pair. And that's the standard position of the vector. And the book even says that this is the position vector. So this would be the position vector for v. And I could do the same for u. So for u, I would take the terminal minus minus the initial, and again the terminal minus the initial, so -4 minus a -5. Okay, so then I could rewrite this as 2 plus a -4 and -4 plus 5, and so u here would actually be in this case -2 for the x and 1, +1 for the y. And so this would be the standard position for this vector here. So this would be over 2, up 1, and then what I got here is that same vector. This is the same vector here as this vector. It's just positioned at the origin going to that ordered pair. And so what's really nice is when these vectors are in the component form, a lot of things are really easy. Okay, so let me show you just a few of the things that are really easy to do. So the magnitude here, so let's say vector v is v1, v2, and these are the two components for vector v. Then the magnitude of vector v is equal to the square root of v1 squared plus v2 squared. Okay, again, this is using the distance formula, but now the initial points are 0, so v1 minus 0, v2 minus 0 would just reduce down to this. So if it's in component form, then you just square each term, add them, and then take the square root, and then you get the magnitude here. Okay, so let me do the magnitude of v. would just be the square root of 2 squared plus 3 squared. So this is the square root of 4 plus 9, which is the square root of 13. See how easy that is? And then the magnitude of u here would just be negative 2 squared plus 1 squared. So this would be 4 plus 1, square root of 4 plus 1, which is the square root of 5. And so those would be the magnitude of those two vectors. Okay? Now here's the really beautiful thing about this. When they're in component form here, so let's say this is adding vectors in component form. Okay, so what we did before, if you remember, we used that parallelogram rule where we took and put this, so this is, over 2 up 1, over 2 up 1, so over 2 up 1, this is the parallelogram rule, and then this one is over 2 up 1, so over 2 up 3, so over 2 up 3. So this would lead to the same thing, okay? So the resultant vector, the sum of those two vectors would be this vector right here, which is actually right on the axis. I didn't mean for it to be like that. But basically what you get is this really, really nice rule that if these are the components of the two vectors, okay, then v plus u is just going to be the sum of the x component and the sum of the y component. That is really, really nice. Okay, and so this really beats having to use like the law of cosines and the law of sines to find the magnitude and the direction. Okay, so let me just do the example that I have here. So the example I have here is that v plus u is just going to be equal to 2 plus 3. 2 comma 3. This shouldn't be plus. 2 comma 3 plus the u is negative 2 comma 1. Okay, so that should be 2 comma 3 there. Very messy. But what I'm going to do here then is just add the x. So 2 minus a negative 2. And add the y is 3 plus 1. And then you see what I get here is 0, 4. And that is actually the component vector. I'm sorry, that's the resultant vector of u plus v. Okay? And so you get it in component form, and it's so easy then to find the component form of the sum of the two vectors, and it just completely avoids the law of sines and the law of cosines. This actually makes good sense too, because if this is the one-ordered pair, then if you're going to put this arrow on it, then you're just adding the other the components of the other vector to get to the endpoint. So this actually makes good sense. Okay, so let me do one more like that. Just make it a little bit bigger. Okay, and maybe I won't. Let me just. I don't know. We'll do. I'll do this one, and I'll say v is. Let's just say 1, 4. Oops. Sorry, it wouldn't be that. I meant 4, 1. Or let's say that's 4, 2. So 4, 2. So in other words, this is 4 and that's 2. And then I could say maybe this vector is we'll say this vector u, so this is vector v, this is vector u, and let's just say vector u is negative 5, 3, something like that. Okay, so if I put this on, we do the parallelogram rule, so this on here would be like this, and then this one here would be kind of like this, and then the resultant vector would go from here up to here, and then what we would be using would be the law of sines and cosines like we did in the last chapter, but now I'm just going to add the components. Okay, of 4, 2 plus negative 5, 3, and 4 plus negative 5 is negative 1, 2 plus 3 is 5, and that's this component here. This would be negative 1, 5. Okay, and so this is such a nice, easy way for adding two vectors. Okay, now let me show you another thing. This is adding vectors. Let me show you one more operation here, and that is scalar multiplication. So what do I mean by scalar multiplication? This is just taking a number and multiplying it times the vector. Okay? And what this means is you're taking the number and you're multiplying it by this vector. We'll say it's v1, v2. And what you're doing is you're just multiplying the x, or the x and the y components by whatever number this is. So k v1, k v2. Okay, and the reason this is called a scalar is because this number scales the vector out. Okay, so let me just give you an example. We'll do this vector here. So let me take, I'll just take 3 times v. So this would be 3 times 4, 2. And so this would be 12, 6. And so what this does is it scales this out so that you have 3 of these arrows next to each other. And this would be the 12, and this would be the 6. And I probably didn't do that exactly accurate here, my drawing, but this scales this vector. It makes it 3 times as long. Okay, similarly, if I did 1/2 v, this would be 1/2, 4, 2, and that would be 2, 1. And that's half the size of the vector, right? This would be 2, that would be 1. So it's making the vector half as long. So it scales it down. And then let's say I did negative 2 times v. This would be negative 2 times 4, 2. And this would be negative 8, negative 4. And so negative 8, negative 4, it would be taking this v and it would be bringing it backwards and then scaling it out twice. And this would be like negative 8, and down here would be negative 4. Okay, so if it's a negative number, it's going to take the vector and scale it in the opposite direction. In this case, it'll scale it out 2 times the length, but it'll be 2 times the length in the opposite direction. So that's scalar multiplication. And so scalar multiplication allows you to take a vector and scale it to whatever length you would like the vector to be. So this is really nice. Really nice stuff. Easy. It completely kind of does away with the need for the law of sines, law of cosines, as long as you can get these component forms, and it makes things a lot easier, as you can see. So really nice stuff here. So I think in the next video I'm going to show you a way of interpreting subtracting two vectors and what it would look like in the diagram.